People could learn more about Fond du Lac, you know?
Right? They probably shouldn't, but they could.
They could.
Is the thing.
And that is a service we provide.
Today's episode is on a thing that people should maybe know about.
Okay.
Actually, have we talked about what we're doing today at all?
No, I know absolutely nothing.
Cool. I barely know what we're doing today because I usually reread my notes right before we do this, but that's not how today worked. Okay, so I majored in computer science and minored in philosophy, which means I can be insufferable about a wide range of mundane topics.
Mm-hmm.
So today we're going to talk about timekeeping and computers a little bit.
Okay. I think I did know that this is a topic we were going to talk about only because I remember making the joke that maybe we were going to talk about Swatch internet time.
Yes. We aren't today. I won't say we'll never talk about that.
Okay.
But we aren't doing that exactly today.
We're not talking about beats.
No. We are going to start with Y2K, I think.
Perfect.
That's how we're going to introduce this topic.
Okay.
We're not going to go crazy deep because I don't know how interesting it'll be, and I don't know how clear my explanations would be either. But what is your memory of Y2K?
I feel like my actual memory of it is I don't really have one. But beyond the nightly news segments that you would see in 1999, where I just have an image of a man in a suit and the upper third box having a funny word art Y2K, and that's kind of it. I don't have I don't know. I was 9, 10 at the time. So the concept of the entirety of the world's economic system may be brought to its knees because of a weird computer thing wasn't super present. I just remember it was something that people were nervous about, and then 2000 came around and nothing happened.
Yeah, that seems pretty close to mine as well. I remember reading it on a placemat in Pizza Hut.
Okay.
On Court Street, if we want to be incredibly specific. And that is my only memory of Y2K at all. Is reading some little blurb on a placemat and then asking my parents what is this?
What's
and
a
they're
Y2K?
Man, we don't know either. It's fine. It's nothing we're going to be able to do anything about anyway, so don't worry about it. All right. Okay, but for those who were not around, I guess maybe we should define Y2K a little bit.
God.
So let's get into the nitty-gritty a little bit. When you are displaying a number, like a year, now we almost exclusively use 4 digits. At the time, it was really common to use 2 digits because a lot of these systems were developed in the 60s through 80s, give or take. And memory's really expensive, especially the earlier back you go. Kilobits become very expensive, even. Just tiny amounts of memory relative to what we work with now were astronomically expensive. So one way to save on the amount of data you're storing is to use a 2-digit year instead of a 4-digit year. So if you have a table that's, let's say, 10,000 records long, do you want 40,000 digits or 20,000 digits that you have to store? So typically what would happen is one of the more common implementations, I guess, would be to store just the number 19 somewhere. And then when you fetch the year that you're looking for, you just slap a 19 on the front of those 2 digits.
Okay.
So that was fine up until 2000, when suddenly that 19 was no longer relevant, stapled to the front. So a couple things happened. Either 1999 would roll over to 1900 that was somewhat common. So that 99 would just add 1 and then go to 00.
Yep.
Or that 99 would go to 100, and then you would see a year displayed that was 19100. So the year 19,100. Yeah. Because, again, they're just stapling 19 to the front of the number.
Yep.
99 plus 1, 100, 19, 100. Yeah. So, like you said, at the end of the day, not a ton of bad things happened because a lot of people spent a lot of time figuring it out ahead of time.
Because this ultimately, like the Y2K computer problem, like this appending the 19 and not rolling over to 2000, like this wasn't like a thing that we discovered in 1999 as a problem. Like this was kind of a known thing, right? Like we at least knew slightly that this was going to cause some problems. We just maybe didn't know to what extent until we got closer to 2000.
For sure. And it's more likely to be a problem the further back the system was developed.
Yeah.
And one of the issues with that is if you have a critical system somewhere, something that like has to work the exact way it's working, and it's very important that it always does that exact thing, like payment systems, air traffic control, like those kinds of systems, you tend to not fiddle with them too much.
Right.
Because it's really important that it doesn't break. And once you start pulling levers, something might break.
Yeah, it wasn't one of the big concerns, the like the nuclear power plants and like military setups as well, right?
Yeah, all that stuff.
Yeah.
Those are all things that like once they're written and they pass QC and everyone's like, cool, this works exactly as we need it to without issue, you don't want to touch it.
Right.
And the longer that thing sits there, the less people remember how it works and why it's there. They just know that's the beige box in the corner that you don't touch. It just does the thing that it does, and no one ever looks at it. Because if you touch it, you might break it, and then the whole thing goes down. So yeah, this was definitely an anticipated problem. But there was a lot of kicking the can down the road, because do you want to be the guy in like 92 who touches the payment system and breaks it, and now the bank doesn't work for 9 days?
Yeah.
You don't. You want to wait until circumstances force your hand so you can't be blamed for that.
Right.
So yeah, as you said, not a lot of terrible downstream effects. I did find one kind of fun one, and this just gives an idea of like the kind of errors that can happen with timekeeping. Is there was a video store in New York that did not have a fix in place, and an individual returned their tape, their VHS tape, I assume, given the time, and that date rolled over, and their internal system generated that tape was well over 100 years due, and assigned a late penalty of $91,250.
Jeez.
Whoops. Okay, so that's kind of like super rough overview of Y2K. Now we're going to shift gears a little bit, and we're going to talk about Unix time.
Oh, okay.
Does that ring any bells?
I mean, the phrase does. I don't quite know what it means, though.
Okay, so time... Yeah, man, we might end up doing multiple episodes on weird time stuff from like both the computer science angle and the philosophy side, honestly. Time is a nightmare. Time zones are a nightmare. The way we keep track of time as a species globally is just a real cluster. Tom Scott has a good video on time zones. Check that out. It's a couple minutes long. It's tragic. Like leap seconds and all that nonsense is just a mess. So you kind of mentioned one of the solutions to this is like the internet time thing, where it's like, what if we all just ignored the sun, and just all used the same numbers because we made it all up anyway. Unix time is kind of in that vein. So the idea is that we're going to store time as a number. And we're starting at January 1st, 1970. Midnight.
Okay.
It was a Thursday. So
To-
what we
to
do,
you, it was only a Thursday.
So what we do is we start right there at midnight, 000000, January 1st, 1970. If we want to keep track of time moving past that, we count seconds positively. If we want to look backwards in time, we count seconds in the negative. And that way, we can just kind of do the math to figure out what day it is.
And is it always seconds?
Yes.
Okay.
Yes, asterisks. Just slap an asterisk at the end of everything we talk about today, because I'm going to have to simplify things to the point that it's kind of wrong for it to be, like, reasonably understandable.
Okay.
Without a lot of nonsense. So, for our purposes, yes.
I appreciate that.
That is it. And the January 1st, 1970 is known as the Unix epoch, which is just fun.
Yeah, that's good.
So typically that number is encoded as a signed number, like we were saying. So it's a number that can either go positive or negative. And to kind of piece together why this is important, I'm going to have to teach you how to count in binary.
Oh, no. Okay. All right.
It won't be hard. I promise it won't be super hard. It'll be pretty easy. I'm going to put a thing in chat here, but then we're going to talk through it since, podcast or whatever.
The amount that I know about binary is mostly from puzzle games that simplify it to an extreme degree. So I am a little curious to see how well this actually ladders up to the whole zeros and ones that I have interacted with in the past.
Yeah, so at the end of the day, everything digital is just zeros and ones. Everything, which is
Frightening.
wild. Yeah, like colors, images, numbers, letters, time, everything is a 0 or a 1.
Yeah. Are we maybe preempting a future episode, but are you going to talk about bit flipping at all?
We could do a cosmic ray bit flip kind of thing. Yeah, we could do that.
Okay.
It probably won't come up in this one, but we
Okay.
could totally do an episode on bit flips.
Yeah, that
Bit flips, and there's
their
tons of
discovery
weird stuff.
and their just general shoulder shrug in the scientific community of we've tried literally everything else. It must be it must be the cosmos.
Yeah, man, there was one with Super Mario 64 had a speed run that there was a suspected bit flip. There was a plane, I think, that had some issues. Now that I'm thinking about it, that was also a suspected bit flip. And this, I haven't looked into this in a long time, so this might be just me talking out my rear end. But I think I remember reading that some of the reasons some of these critical systems use really outdated technology, like missile launch stuff, is because the physical bits are bigger, so they're harder to flip.
Jeez.
Because they have more mass.
Great.
Yeah.
That's not
stuff like
scary
that.
at all.
Yeah. And yeah, you have to worry about that when you're leaving the app. Yeah. We'll do an episode on bit flips.
Yeah,
I'm
bit
sure
flips
I'm
will be
getting
fun.
some of that wrong. Yeah. Okay. So yeah, everything comes down to either a 0 or a 1. And which kind of doesn't make sense. So the only way to make that information usable is if ahead of time everybody knows how many zeros or ones they're looking for. Because if you think about it, it's just a bunch of numbers in a row.
Yeah.
It's kind of like, I know we did some stuff with ciphers in the past, manually
you have to have the
encoding
key.
messages. Yeah. So you same kind of idea. You need to know what you are expecting out of that string of numbers to make any sense out of it.
Right.
So here is 1 through 15 in binary. I have an analogy for this that will work for you and everyone older than us. I'm now realizing my analog analogies won't translate to a younger audience. But I have an old analog brain, so that's what we're going to do. Do you remember, like, manual analog odometers?
Oh, yeah.
So you got all the numbers on a little wheel, and they scroll
over.
Up. Yep. And then when it hits a 9, it goes back to 0, and the adjacent digit goes up by 1.
Yeah.
So binary counting is the exact same, except instead of 0, 1, 2, 3, 4, 9, it's just 0, 1. So that dial, instead of having 10 digits on it, now just has 2.
Okay.
So if we look at, we're going to record numbers with 4 characters. So if we look at 0, that would be 0, 0, 0, 0. Then we have 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and we just kind of keep going from there. So anytime the rightmost digit hits a 1, it goes back to a 0, and the next one increments.
Okay.
And we keep doing that.
Yeah.
All the way up.
Yep.
And you can kind of see the pattern there as that one sort of tracks from right to left, and then another one gets introduced on the far right, and that sort of tracks from right to left. And we keep doing that until we hit all 1s.
Okay.
So, does that kind of follow?
Yeah.
Enough?
Yeah. It follows enough. I am curious what happens. There is no 16?
There is not a 16. You did notice that. So yeah, we have 0 is 4 zeros, 0, 0, 0, 0, and 15 is 1, 1, 1, 1. So, if we go to 16, what might happen?
I mean, it would just basically revert to 0, right? It would be 4 zeros.
Yes. And you have now discovered what is called an integer overflow.
Okay.
Which is maybe a thing we've talked about off pod in the past.
Yeah.
So that's when, like, in this instance, we're expecting 4 digits to exist. But to go to 16, we would need a 5th digit.
Yes.
But since we've already decided ahead of time, well, this is only 4 characters wide, like you said, instead of adding that 5th digit, they all just roll back to 0.
Yeah.
So the way numbers are stored, they're either signed or unsigned. So we're either keeping track of, is this thing positive or negative, or is it not? So looking at the chart I sent you here, we have 16 numbers displayed, 0 to 15. They're all positive.
Yes.
But if we use those same 4 bits, those same 4 characters to display numbers, and we wanted to include negatives, we kind of have to lop off one of those numbers and use it to keep track of if we're positive or negative.
Yes.
So then our range cuts down from 0 to 15 to, what, -7 to 14, 15? You get the idea.
Yeah.
The range is still, well, it's -1 now, but we go from negative to positive.
Mm-hmm.
So if that was the case, we would go from, like a positive value to a very deeply negative value. And now we're going to go back to Unix time, where we are counting seconds upwards from 1970.
Yeah, that's a lot more than 15 seconds.
It's a lot more than 15 seconds. That number gets real big. Gets like fuck off big in a hurry when you're counting seconds over the course of decades. In a lot of old systems, Unix time is stored as a 32-bit signed integer. So instead of those 4 little numbers going across, we have 32 different numbers, different characters we can keep track of zeros and ones with.
Okay.
And since it's signed, it goes from a negative value to a positive value, because we need to be able to count backwards in time, because sometimes we're interested in things that happened before 1970. So this number might sound familiar. A signed 32-bit integer can go from roughly -2.147 billion to positive 2.147 billion.
Oh, is this is you put it in the books. We are 28 minutes into this recording and we have hit time to RuneScape.
Correct. I was wondering if you would catch that or not. Uh-huh. So yeah, that's our max cash stack.
Yeah.
2,147,483,647.
Okay.
It's also the most XP you can have in a skill for the same reason. It's because that's as big as the number goes. It doesn't go any bigger.
Okay.
Exactly. So, what happens when the number of seconds can't get any bigger?
Time stops?
Time stops. So, if we take January 1st, 1970, a Thursday, and we add, I don't know, for the sake of argument, let's say we add roughly 2.147 billion seconds to that, then we get 3:14 a.m., January 19th, 2038.
That's coming up.
That's not super far away. So we have, was that 14 years less than 13 and change?
Yeah, 13
to get ready for Y2K2. Welcome to the year 2038 problem.
It sounds worse.
The apocalypse. It is going to probably be worse.
Yeah, okay.
This is why it's worse. So the issue with Y2K was just storing that 4-digit number as a 2-digit number. There were some hacky ways you could fix that, and a lot of those systems were probably going to get replaced anyway, so it didn't really matter. One of the things people did was say, like, oh, if the number is under 25 or 50, then append a 20 to the front. And if it's over 50, then append a 19 to the front.
Okay.
And that was like a real Band-Aid thing of like, well, we can't make it store 4 digits, so we're going to manipulate the way we read the 2 digits. Which again was just another like kick the can down the road sort of thing.
Yeah.
And some of those fixes came up in 2020 and 2025. Were both numbers people use for that. So there have actually been some like downstream Y2K impacts in the 2020s, which is fun.
Yeah, that is fun. Terrifying, but fun.
Yeah. So this version, the year 2038 problem, is a little more complicated because systems are designed to read like 32-bit or 64 bits at a time. And they don't like to do more than that without some techno wizardry involved.
Sure.
And the other issue is, since this is, it's called Unix time because it was, baked into the Unix operating system forever ago. So this is a method of timekeeping that is used in a ton of different programming languages, all kinds of systems, kind of function off of this counting forward or backwards from 1970 sort of thing. So when that number hits, we're going, I don't know. It's going to flip negative since it's signed.
Oh, right. Yeah.
Yep.
I didn't even think about that.
Goes back to like early 1900s. Something like that. So yeah, that's a problem.
Yeah.
The other problem, go ahead.
And it's just like you were saying, it's like built into like language and stuff. It's not even like retrieval of numbers. It's like literally how the internet and software itself is built, right? Like it's much different than, we just didn't, like in the timekeeping aspect, we didn't like build out the 2 to 4 digit numbers. Now we're like, this is built into the actual framework of how we make things.
Yeah, we have to like fundamentally redesign how the clock works instead of, for a lot of things, this maybe won't be a problem. I think the issue we're going to see, and we have seen already in some cases, is embedded systems. So think of anything with a microchip that doesn't have a screen on it, basically. or even if it does have a screen. Like things that aren't running a full operating system, things that are executing small bits of code arbitrarily, like a thermostat, let's say.
Okay.
So my thermostat, super basic. I don't know, it was like $30 or something. It's not a smart one. It's old. It's sitting on the wall. It does its job. But I have noticed, like, if I turn the air conditioner on and then it cycles off on its own, and then I drop the temperature a little bit to turn it right back on, it doesn't always kick back on right away. Sometimes it takes, 5 or 6 minutes. Same thing with the heat. And that is because the thermostat is programmed to not cycle those appliances on and off super fast because the compressors and things can be damaged by that.
Mm-hmm.
So it's keeping track of time in between the last time it activated and the next time it's being asked to activate. And it does a little math, and it says, only 2 minutes has passed, but my programming says at least 4 minutes and 22 seconds has to pass before I can cycle this compressor back on.
Yep.
And both of those numbers come from
Unix time.
Using, yep.
Oh, no.
Yeah. Yeah, yep.
Yeah, okay. So in the like thermostat example here, I have a smart thermostat. So
yep.
If this problem is solved and society is to move forward, hopefully my thermostat, if it makes it another 14 years, will get an over-the-air update, which will hopefully somehow fix this problem. But you're screwed. Like your thermostat is just cooked. Like you're done now.
Mostly, yeah. In the case of our thermostat, yes, we have now created e-waste with my thermostat.
Okay.
If it's a system that is more important, there are fixes that can be done, but they're all going to be like a little more situational than the Y2K fixes were. Like a lot of those chips have onboard memory that can be accessed and flashed, and those things can be updated, but yeah, like is now we're looking at like how much documentation exists for the firmware of this thermostat that was made in 2002, and is it a thing we can update easily or not? In a lot of cases, you're just going to throw the thing away.
Yeah, yeah, it'll just be over.
But that's like maybe not what you do if you have like a really expensive CNC machine, or I don't know, something that runs your payment processing server at a bank that's
right,
hasn't been touched for 40 years.
Oof.
Yeah. Yep. So anything made in like the late 2000s is probably already running on 64-bit hardware, and a lot of these like function calls have been updated to work with 64 or 32-bit values. So it's yeah, man, I don't know. It's going to be weird. There's not a great way to know like what's going to break and what's not. Even if you go back to like, if you have an old Android phone sitting in a drawer, like Android, 3.4 or 4.3 or earlier, I mean, I want to say 4.3. I probably got the version number wrong. Old Android phone, if you take that and you set the calendar to like 2039, it'll brick the whole thing. The whole thing will crash.
Really?
Yeah, they have been updated since then. So if you've received updates on it in the last number of years, then it might accurately display the time now. But that was one of the early ones. But yeah, man, there's so many things that use time that you wouldn't necessarily consider. And that like anti-lock brakes, those are keeping track of time.
Oh, I hate that.
To trigger that. So, yeah, like stuff like that. Stability control, traction control, all of that stuff is like taking data from sensors and comparing that data to data that happened shortly after that or shortly before that to determine if you're in a slide and if that traction control needs to change or ABS needs to kick in. Those are all time dependent. Anytime you are doing really any communication over a network, that's all time dependent to some degree. So routers, access points, IP cameras, all that kind of stuff is all using time in ways that you would maybe not think of as a layperson from the outside looking in.
Jeez. Okay. But so the fix is just going from 32 to 64.
Yep. And finding a way to do that.
That makes a 2173 problem. Is that? It's like much bigger than that, I suppose, right?
It is wildly bigger than that.
Yeah, it's not double. It is exponential.
Yeah, so we went from 4 bits. We were able to count to like 7, I think, is the positive integer. I think it's -8 to +7 would be 4 bits. And then 32, we know, goes up to
2.1
over 2 billion.
Yeah.
So now that we're pushing to 64, and a lot of things are already on 64 bits, that gives us like a good amount of time after the heat death of the universe.
Okay.
So that can has been sufficiently kicked, I think, once we hit the 64-bit. It's something like is pushing 300 billion years.
Okay.
From now. Yeah, like it's no longer a thing we're worried about.
All right.
But we don't really know. We're not going to know what's going to break until it breaks in a lot of cases.
Yeah. Oh. Yeah, and like I guess it is like a weird, like the thermostat and like the anti-lock brakes are very mundane examples of this. And hopefully, I mean, you would hope that larger, more important systems like, you know, large power grids and like regulation software for that and all of those things will get their updates maybe faster than 1999 to 2000, but still, like the very small level of I'll have to get a new furnace in my house is annoying, but ultimately is something that hopefully will be taken care of. And then once you replace it, it is good to go, at least from the timekeeping aspect forever. But that's a lot of e-waste. That seems like there should maybe be some preparations ahead of time in a very like public facing way to deal with that.
Yeah, so I just learned about this relatively recently, which kind of surprises me. Like I these function calls that cause this problem I use in code I write frequently. And I have not encountered this error exactly, but there's the thing that worries me is just like with Y2K, it was pretty clear if the thing you were using kept track of the year or not.
Yeah.
Like the anti-lock braking system doesn't need to keep track of what year it is.
Right.
It's just concerned about the distance between 2 points in time. And it uses this method of counting seconds to keep track of that. But before we talk today, I'm going to guess you had never considered the relation of time to how anti-lock brakes function or how your thermostat functions.
No. And it makes a lot of sense, right? Like these are no longer mechanical systems in the same kind of way. Like they still have mechanical functions, but you know, one of our cars is an EV. So like now, like thinking about that, like we're not even talking about anti-lock brakes in the same kind of way anyways. And then knowing that my car is mostly just a computer and that, you know, I'm sure that this is not the case, but you know, 2038 rolls around and that car is just bricked. Like it does not move because it has hit like a timekeeping error with how it wants the engines or the little motors to function.
Right. And some of that's also going to depend on like the error handling that was put in place when that system was designed.
Right.
So I've written a few projects that are like meant to be used by not me humans. And when I do that, you kind of have to account for like, what are the ways this could break, the software could break, and how do I deal with it once it's broken, and how do I communicate that to the user? But like, I don't know what kind of error handling you put into a thermostat.
Yeah.
Like, does it just, some of these things might just like boot loop, I could imagine. where like it hits one of these errors that is unexpected. It hits an overflow error. And so their methodology at the time was just like, oh, something weird happened. Just reboot the system. It'll be fine. But it won't be fine because it's already 2038 and it's going to hit that same thing every time. So yeah, like stuff might just boot loop. Some things might be fine. Some things might. Yeah.
This kind of reminds me, I was trying to find it in the background here, but every once in a while I run into this error. I haven't had it in a really long time. Oh yeah. Okay. So I've had the error where something goes on in my Mac and it decides that today's date is December 31st, 1969, which I guess is back to that.
1 second before the Unix epoch.
Yeah. Yeah. Okay. Yep. So that makes sense. So then does your thermostat just get into like a weird death loop? Does it just go back to, it just replays the same 70 years over and over again? That seems bad.
Yeah. Yeah, that's the fun thing is these can all break in like new and exciting ways.
Yeah.
Where the Y2K thing felt a little more quantified to me. Of just like, well, we have a pretty good idea of what's using this, how it's using it. And typically that's being displayed somehow. Like there's some amount of feedback between the system and the user about what year it is.
Yeah, and
that
I mean,
won't necessarily be the case here.
And we're talking about like fundamentally different internets. You know, like the 1999 internet versus what we use the internet for now is so drastically different, and how we use it and how we, you know, how we end up needing to use time in that way. Like at every one of these calls we start with, we just go to a website called time.is, find out how, like, you know, sync up our times so that our audio tracks play nicely. But every single time it like displays, well, you're either plus or minus the amount of internet time that we think it is. And that is an incredibly mundane use of timekeeping on the internet. But, you know, if I just look around, I mean, who knows? Like my monitor might need to be keeping track of time for some reason, and this time rolls around and it's just done. You know, like I don't get an over the air firmware update on my monitor because the time is coming to an end.
Yeah, there could be like a refresh rate setting, or who knows? Yeah, or like, I mean, an old DSLR camera that embeds a timestamp into the metadata of the image. Yeah. Yep. Like I say, if that's a 32-bit system, then I don't know. Yeah, man, I don't know. It's gonna be fun. I'm kind of thinking about like maybe going down this as a career path slightly. I might keep tinkering with these ideas because something tells me there will be money to be made as a contractor if these are problems you can solve.
Yeah, funny. Like .com boom, but internet time. Incredible. Well, that's a devastating but very normal end to civilization, I suppose.
Those are my go-tos.
Yeah,
mundane and catastrophic.
Luckily, it sounds like some systems are being updated to deal with this, and hopefully the important ones are too. But
yeah, and I don't anticipate this being like crazy apocalyptic. Because again, the closer we get, the more people are going to be aware of it, and the more people are going to be willing to spend their budget to solve this problem once it's looming.
Sure. Yeah.
So I think it'll be like I don't know, maybe get some extra cash out of the bank and do your grocery shopping ahead of time, because maybe payment systems will be weird for a couple of days or stuff like that. Maybe don't plan air travel over that time. Whoops. Because we could do a whole episode on like how many air traffic control systems are still running on like Windows NT or 95, because it's just like, oh, here's this critical system that we don't want to have to rewrite because then it might break. So we're either piecing together this incredibly archaic hardware, or we're running like 4 virtual machines containered inside themselves to get this thing to function the way it expects.
Yeah, because the world economy cannot handle like a good old 2-week bring all the airplanes down so that we can have a hackathon to fix this problem.
Right. I remember, I think there was an airport in France that was recently redone that was using some like 95, 98 air stuff, or like a lot of HVAC systems run on really old tech. Another one I remember reading was like a school district that had like a Windows 95 machine that was controlling the thermostats at every building in the district.
Oh my God.
So, yeah, and that just sits in a closet and everyone knows not to touch it.
Right.
And it's just worked for 20 years. So, like, once it stops working, then it's going to be who's around to track down what actually happened and diagnose it. And then, is this a thing we can fix in place, or is this a thing we have to get new hardware for because of the way this reads memory? It doesn't want to use a 64-bit number, or it's going to be a thing.
Yeah, and you can see how it goes, right? Like, this is a problem that is 14 years from now, and there is in I don't know, like in the mind, you can say, oh well, 14 years, like that's plenty of time to solve this problem. There's a lot that's going to happen there, but we're 14 years from now is actually not that far away when you're talking about having to redo an entire HVAC system for your small elementary schools, and like having to do a tech overhaul on those things just because like otherwise the heating and cooling doesn't work. And there's no list, right? There's no, like, especially stuff like that that's not like actively networked. Like no one is sitting there thinking, yes, this system runs Windows NT and therefore we need to upgrade it at some point. Like that just sits in a closet. Like no one is thinking that we need to upgrade this system because it works fine. What could possibly happen in the future that could decimate this computer in a way that would destroy everything?
Yep.
Great.
And there's so many devices too. Like there are so many more embedded devices that exist now than did like in the Y2K era. Think about anything in your life that has an LED in it. That's probably controlled by a chip that's maybe keeping track of time.
Yeah, and I wonder, we're now in just like rampant speculation zone, but I wonder all of those things, like as we kind of like trace, I'm very curious about the past probably, I guess, 20 years or so of like the Amazonification of everything, and how Amazon as a storefront has like moved beyond just selling books and then had like its Amazon brands, and for the most part had like things that you could generally trust. But now it has mostly just become a like Chinese e-waste kind of thing that is just
factory.
Like, like absolutely flooded with things like this. And when we're talking about, that's something that runs either a 32-bit or a 64-bit, with the initial premise being, will we use a 4-bit system to save on memory? Like when you're making little widgets that you're selling for pennies on the dollar on Amazon, are you going to push for that slight amount of memory to like do that? Or do you just pick the smallest microcontroller you possibly can, shove it into a thing and hope that it works out?
We are going to find out.
Yeah, great. Cool.
I guess the quote unquote nice thing about that is most of that stuff's going to be dead before then anyway. So
yeah.
It probably won't be an issue. Like the way the time dimension has worked in this case, it's a lot of stuff's not going to make it to 2038. Probably.
Yeah.
But it depends on how that stuff is replaced, because maybe it gets replaced with a different 32-bit thing for ease of replacement. So, yeah, I don't know.
Yeah, just one last incredibly morbid thought as we leave this, but I just, the thought that just came to me is, what are we going to do about pacemakers?
Man.
Just like medical technology.
We should do an episode on how weirdly unregulated or poorly regulated some of that medical stuff is. Yeah.
Well, okay. Anyway.
I promised not to make you too sad, and here we are.
Good. Well, I mean, that was
I think it's neat, though.
Yeah, no, like, it is cool.
It's definitely a fascinating thing to try to wrap your mind around, and it's a different way to think about time.
Yeah,
which is also fun. Like we are going to do a weird time episode where we talk about like the concept of now and what time is, if time is anything.
It'll just be Spaceballs references the entire time.
When will then be now?
Yeah.
Yeah.
This is fun. I had never really thought about this beyond knowing that it was a concept, but it is very funny to see us dig our own holes here and then have to dig ourselves out of it just because Moore's law, mostly.
Welcome to humans.
Yep. Awesome.
Yeah, as soon as I saw a thing that I was like, oh, I can talk about Y2K and RuneScape at the same time. This is a topic we have to touch on.
It's basically your wheelhouse.
Yeah.
Awesome. Yeah, this is fun. I mean, honestly, 2038 is a much more compelling doomsday than 2012 is. You've sold me on that.
And also the phrase epocalypse is good.
Ooh,
so,
that is good.
It's the Unix epochs, so it's the epocalypse.
I'll have to see if there's a Mayan calendar related to this one.
We can only hope.
Awesome. I don't think we have actual outros for this. So, hey, this is Infodumping, and thanks for listening to this fun bonus episode. What do you do? If you like it, you like and subscribe and all of that fun stuff, and 5-star reviews, podcast player of choice. Gordon Hamburger is the website. I'm Phil.
And I'm Logan.
And that's it. We'll see you later. Hopefully next month, when we will be talking about beans, molasses, and how they are very important for a devastating problem in the Boston area. All right. See ya.
Bye.